Hello and welcome to today's video on Kirchhoff's voltage law. In this video, we'll be discussing the basics of Kirchhoff's voltage law, why it is important in circuit analysis, and how to apply it to solve circuit problems. Let's look at this circuit. So KVL, right? Kirchhoff's voltage law. This is a fundamental law of circuit analysis. What does it state? It states that at any instant around a loop in either the clockwise or anti-clockwise direction, the algebraic sum of voltage drops is equal to the algebraic sum of voltage rises. Too many technical terms. Let's break this down. So let's look at this circuit. Over here, we have three resistors in series and there is a voltage source connected to it. So this is a closed circuit. Here, current is going to flow out from this, say, battery through the resistor R1, then resistor R2, then resistor R3 and come back. So if we notice, all the three resistors are connected end to end. So this means that the same current is going to flow through R1, R2 as well as R3, which is why they are said to be connected in series. KVL is extremely useful for analyzing complex circuits containing multiple loops. But for a better understanding and to see how to implement KVL to any circuit, let us consider a simple circuit with a single loop. So here, the first step to implement the KVL is to consider an arbitrary current direction. Intuitively, in this circuit, we can consider that the current is coming out of the positive terminal into the circuit. So this is the direction of current in the circuit as discussed. Now, since the current is entering R1 in this point, we are going to consider it to be a positive terminal, and since it's leaving R1 at this point, it is considered to be negative. The same thing is applied to R2. So current enters here and this is positive, this is negative. For R3 again, consider this to be positive and negative. So now the first step is we've considered an arbitrary current direction and we have labeled the voltage direction in the sense we have marked the terminals with positive and negative sign and we can consider the voltage direction. So here always the voltage direction is considered or the voltage drop is considered from positive to negative. So this is VR1 or rather V1, this is VR2 and this is VR3. Then for the source, V source, this is positive and this is negative. So the direction is going to be like that. So that is V source. Step 2 is to assume a clockwise voltage drop direction. Conventionally, we can do this. So we are going to assume a clockwise voltage drop direction. Now we are going to compare the direction of each of these voltage drops on these resistors and also the V source and the direction of the voltage drop which we've considered here. Looking at this, we can frame our KVL equation. So in this case, the direction of VR1 and the direction that we have considered is the same. So we can say plus VR1, meaning positive, because both of them are in the same direction. Look at VR2. VR2 and this loop direction are again same. So this is plus VR2. Similarly, VR3 and this loop direction are the same. So it is plus VR3. But if we consider this loop direction, this moves upwards in this branch, whereas the voltage drop over here is downwards. So they are opposing each other, which means I have to consider it to be negative. So that is minus V source. Now, as per the, the KVL statement, the sum of voltage rises and voltage drops within a loop should be equal to 0. So, that's how simple it is to frame a KVL equation for a loop. Just follow the two-step method. Having framed the KVL equation, we can now solve this circuit to find out the different parameters like I source and the voltage drop across each of these resistors. So, how can we do that? We know from Ohm's law that V is equal to I into R. So, in this case, VR1 is nothing but I source into R1. So, I source into R1 is VR1 plus VR2 again is I source into R2 plus VR3 will be I source into R3. We can take this V source to the other side of the equation where it becomes positive is equal to V source. So now we can see that we can take I source common, R1 plus R2 plus R3 equals the V source. So here R1 plus R2 plus R3 is nothing but V source by I source, which is nothing but the total resistance of the circuit, because after all V by I is nothing but R. In this case it represents the total resistance of the circuit. Since these resistors are connected in series, we can find out the equivalent resistance of the circuit by just adding up the resistors. So R equivalent in this case is R1 plus R2 plus R3. So there you go. Using KVL, we have established that for resistors connected in series, the equivalent resistance can be found out by just adding them up. We can now just substitute the values and find out I source. So I source is nothing but V source over R1 plus R2 plus R3, which is nothing but 12 divided by 30 plus 20 plus 10, which is 60. So that's 0.2 amps. So that is I source. Having found I source out, we can actually find out VR1, VR2 and VR3 by substituting I source's value as what has been found out and the values of R1, R2 and R3 which is given from the circuit. So here VR1 becomes 2 volts and so on. So this is how we can analyze a circuit by framing the KVL equation and applying Ohm's law and finding out the different parameters. We can do this in a simpler way by applying the voltage division rule, which we'll be discussing in our next video. Let us now consider a two-loop circuit. Let's apply the same two steps that we discussed before. This time around, we have to consider the arbitrary currents and the clockwise voltage drop direction for each of the loops. So here we can see there are two loops. Loops as in a closed path. So this is loop 1 and this is loop 2. So the first step says consider an arbitrary current direction. So let me consider the current direction to be like that for this loop and the current direction to be like that for loop 2. So here This current is entering R1 over here. So I'll mark it as positive, I'll mark this as negative. The same current is going to enter R2 over here, and it is going to leave R2 from here. So this is positive, this is negative. Now, let me call that as current I1. Say this is I2. So I2 enters R3 over here and leaves R3 over here. It enters R2 over here and leaves R2 over here. So now let's consider this current to be I3. Let's mark the voltage drops. So the voltage drops should be in the direction from positive to negative. So that is V1. This is one drop. So let's just look at loop 1 first. In this case, V1 and say V2 are the two drops. I should call it as VR1 and VR2. And this is the first voltage source, V1. So let's look at the drop over here. It is from positive to negative in this direction. So if we consider this loop 1 alone and try to write the KVL equation for it, the second step here is we need to consider a clockwise voltage drop direction. So now let's look at the arrows and try to find out the sign of each of these voltage drops. So over here, VR1 and the direction that we've assumed is in the same direction. So it will be plus VR1. VR2 and the loop direction is again same. So plus VR2. But the loop direction that we've assumed and the voltage drop of this source is opposing each other. So minus V1 is equal to 0. So this becomes my first KVL equation for loop 1. Here we are going to have two KVL equations because there are two loops. Applying the same thing for the second loop, we've already marked the terminals. Now let's mark the voltage directions, always in the direction from positive to negative, and consider a clockwise drop direction. So the two steps are done here. Now let's compare the direction of the arrows and frame the KVL equation. So if we consider VR3 and the direction of the arrow that we have assumed over here, they both oppose, therefore minus VR3. Then the direction of VR2 dash, because this is VR2 from loop 2, right? Not loop 1. So VR2 dash and the direction that we have considered here, again, they are opposing. So minus VR2 dash, and this direction that we have considered and the arrow for the voltage source V2 are in the same direction. So therefore plus V2. All of this put together should be 0. So these are our two KVL equations. Equation for loop 1 and this is equation for loop 2. The solution to the two-loop circuit can be done using the Ohm's law like we did for the single loop circuit, or it could be done by applying the mesh analysis, which will be discussed in one of the upcoming videos. So stay tuned. Thanks for watching this video. Hope it was helpful. Please do subscribe to my channel.